So far, we've presented many plausible new answers to the major questions facing current cosmology theories. But there's another element in the makeup of the universe that stirred up quite a lot of speculation, and that's the thing we call gravity. Now, many physicists consider it to be one of four fundamental forces of nature. Three of the forces have to do with ordinary matter and are well understood. We're most familiar with the electromagnetic force, which acts on everything we can see around us. Now, two other forces are called the strong force and the weak force. They only act on matter at the subatomic level, but they perform functions that, among other things, make life such as ours possible. They're related to each other by a theory called the Grand Unification theory, or GUT, which proposes that they all emerged from a single force in the high energy of the Big Bang. Now, many physicists who consider gravity a fourth force have tried to integrate it into the GUT to produce a TOE, a theory of everything. Well, so far, the efforts to make the mathematics make sense and to find the messenger particle it would need, called the graviton, they haven't been successful. So a good place to start looking for a reasonable theory of universal gravitation is Albert Einstein's general theory of relativity. Einstein suggested that gravity was not a force, such as Newton proposed, but instead resulted from the property of matter to warp and curve the space in its vicinity. The slide shows a two-dimensional and a three-dimensional depiction of how an object affects the grid lines of space. If another object passed nearby, it would follow the curved grid line. It's called a geodesic, and behave exactly as if it was being acted on by Newton's force. Turns out that Newton's formulas, although based on a faulty principle, they work beautifully at relatively slow speeds, and hey, they can take a spaceship to Mars and back without an error. But it's from Einstein's theory that we obtain one of the fundamental facts about the universe. Matter contracts space. In other words, the gravity that we associate with matter comes from its property of warping nearby space into a curved configuration that will follow the gravitational laws. We can see that this is a property of black matter through the gravitational effects of black holes and also the clouds of black dust, or if you prefer, dark matter, which affects the rotational speed of galaxies and bends light when it passes near them. We also see that gravity is a property of ordinary matter. And indeed, the only way we know black matter exists is through its gravitational interaction with ordinary matter. So we can safely say that ordinary matter contracts space to produce gravity. But we need to think about that assertion, however, in light of the description of ordinary matter particles proposed by quantum theory. Quantum theory holds that the particles of the standard model are comprised of energy packets vibrating in space that react with each other and the Higgs field, sometimes as waves and sometimes as if they're solid objects bouncing off one another like billiard balls or shattering each other in violent collisions. The subatomic behavior of ordinary matter described by quantum mechanics is often very bizarre, but it's very predictable and it's well proven. But there's a question, however, about whether the particles contain actual matter as well as space and energy. Well, let's consider what would happen if at the macro level that we live in, if ordinary matter consisted only of energetic vibrations in space with no matter component. Now, if this description of subatomic particles were accurate, there are some questions that come up when we observe how it behaves in the world we can see. For instance, one thing we know is that E equals mc squared. But if there were no matter in a particle to convert, where does the energy come from? We'd have to explain how only particle vibrations could release such humongous energy in nuclear reactions. We've also speculated that collapsing stars will create black marbles of matter without space. But if the ordinary matter was only perturbations in space, where did the black matter come from? And of course, since we know ordinary matter has gravity, we need to explain how a collection of vibrating energy packets would act to contract and curve the space around it in the same way as black matter. So there's a good case that can be made that ordinary matter actually has a black matter component. There's a famous principle called Occam's razor that proposes that when you're faced with a difficult problem, the simplest answer is usually the best answer. So let's apply it here and speculate that ordinary matter particles have cores of black matter. We've already stated that black matter contracts space and causes gravity. Well, we could surmise that the gravitational effect of ordinary matter derives from its black matter content. Now, this speculation solves one of the biggest mysteries in current cosmology. Why does ordinary matter only communicate with black matter through gravitational interaction? If we accept the premise that ordinary matter contains black matter, we can explain that it's only the black matter component in ordinary matter that's interacting with the rest of the black matter in the universe. So, how did the black matter get there? Well, in the previous section, we discussed the creation of ordinary matter during the Big Bang. Most standard descriptions of the Big Bang model propose that ordinary matter somehow just condensed directly from the primordial energy plasma, forming particles as soon as the temperature dropped far enough to allow this to happen. Well, on the other hand, black marble theory actually proposes a process that occurred during the transition from the high energy explosion phase to the lower energy expansion phase. And at the moment when the descending energy reached a critical level that resonated with properly sized smithereens of black dust, vibrating particles of ordinary matter were created. And that's all the ordinary matter the universe would ever possess. By the way, there's a branch of cosmology called string theory that's getting a lot of attention. And it proposes that matter particles are formed from minute entities called strings that vibrate in multidimensional space. And it's tempting to ponder the possibility that the black matter cores could provide the material for these strings. For now, though, we'll leave that speculation for some courageous string theorist and continue with our investigation of gravity. So, at this point, I hope we've made a reasonable case that ordinary matter particles contain a minute smithereen of black matter, whose vibrations perturb space and produce the energy packets that define the particle's properties and lead to its quantum effects. And if this is true, it leads to one final conclusion that we can attribute to black marble theory. We've stated that black matter can exist in the form of black dust and in black marbles. And now we've added that a relatively small amount is associated with ordinary matter. Well, this inventory accounts for all the black matter that exists in the universe. We've also noted that black matter has the property of contracting space and causing the gravitational effect. But at the same time, we don't know of any other process that can cause it. So, therefore, we can come to the conclusion that black matter is the agent of gravity. And it's all we need to explain a theory of universal gravitation. So, once again, black marble theory has provided a simple and logical suggestion to answer the thorny problem of gravity that scientists have been trying to solve for years. So, Now we're near the end of this series that presents this idea called black marble theory. We've tried to fill in some major blanks in the current theory with some new ideas and some alternative explanations. In the last section, we'll wrap up with a brief review and then discuss where the theory may go from here. So I hope you've enjoyed this excursion into cosmology, and I hope you've gotten some new ideas to ponder about its many mysteries. It's been an interesting journey, and I really appreciate your coming along.